friends out there. Yesterday, Zach told me that I talk too fast, so I'm going to try and slow it down a little bit to make sure I'm heard and intelligible.
I don't think I said too fast. I was admiring how fast you speak.
I want to make sure the content is heard. So, I'm Ryan Labello. I'm joined by my colleague, Louis Kale. You've seen some of our passive house projects before. I know Deborah Molis presented UTSC earlier, probably tail end of last year. Today, we're going to quickly compare and contrast 4 passive house projects in the office, really to highlight that there's no one way, one method to making a passive house. But first, why are we here? It's because climate change is the greatest challenge to our long-term survival on this planet. A lot of attention goes to 40% of the world population at risk due to rising sea levels, but we cannot forget about the worldwide droughts, wildfires, deadly flash floods, crop devastation, access to drinking water, it goes on and on. We are already experiencing these effects, and soon the situation will be unrecognizable. At Handel Architects, we believe that passive house can be one of our best strategies to mitigating climate change. And we believe that working in cities is one of the best places to make that large catalyst and that large change. It's where you get your biggest bang for your buck. Passive houses are great everywhere, but we can affect the most people per square foot, obviously, in the carless urban average, and that's where our work at Handel Architects, that's where we focus. And just a reminder, we know that passive houses are well suited to multi-story large buildings, and it's because of this low surface to volume ratio. A single apartment with one facade for 2 people is much easier to achieve on a per square foot basis than a single family home for 2 people that has 6 surfaces. And then this is, you'll see in a second, this is the plan of the Cornell Tech Tower. Note the smoothness of the building shape, not a lot of ins and outs and articulations. Obviously, that's to decrease the number of thermal bridges. Now, at Handel Architects, we like passive house because it is a performance-based standard and it allows us great flexibility to meet varied program requirements, budgets, and client goals. We're going to look at these 4 projects. It's the house at Cornell Tech over here on the left. It's a public-private partnership between Cornell Tech University, Hudson Companies, and the related companies, and it was completed in 2017. Sendero Verde here in New York City. It's a 100% affordable housing multi-building project with Jonathan Rose Companies, L&M Development, and the Acacia Network. Also a partnership with New York City's Housing Preservation Development, a city agency. It is currently under construction in East Harlem. Over here is Winthrop Center, a large, very large mixed-use tower by Millennium Partners, currently under construction in Boston. And then University of Toronto at Scarborough, it's a dormitory, a public-private partnership between Fengate and the University of Toronto. The project is in the very beginning stages of construction. I was the project architect for the house at Cornell Tech. When it was completed, it was the world's tallest and largest. These things tend to come and go really quickly, as you know. Louis and I worked on Cornell Tech together. And then I was also an internal advisor on the Winthrop Tower. And then Louis was focusing on UTSC's facade. So here are the 4 projects, just this kind of a dumb idea, but the passive house, you can see here how flexible that standard is. The kind of building type, the scale, the materiality, they're all different. A couple things just to pull out. You have the house at Cornell Tech here. It's 26 floors, 270,000 square feet. It's not a dorm, it's actually graduate student housing. It has about 500 beds. Now, comparing that to University of Toronto, that's 9 stories, 270,000 square feet, actually the same area as the house at Cornell Tech, but it's a lot more dense. It's an undergraduate dorm and has 750 beds. Sendero Verde, here's the 100% affordable housing project. The tower that is 37 floors, and then 2 lower rise, 16 and 10. And then there's a real robust nonprofit base, community facility base to engage with the city. Winthrop Center is a 1.8 million square foot mixed use project, of which from floors 3 through 30 here are 735,000 square foot commercial office space, which, it's just a portion of the building, but you kind of look at that and you're like, wow, that's the portion that's being passive house. And it's like twice the size of Cornell Tech and University of Toronto, and almost the entire area of all of Sendero Verde. I'm not going to go through all of this. We don't have a tremendous amount of time, but a couple of project challenges. Obviously, Cornell Tech, that was the first time that we did a passive house, and it was also, we're specialists in high-rise buildings, but we had to apply the passive house requirements to the large scale. So that was a project challenge. We had some code conflicts on Cornell Tech, mainly on the mechanical side, but we were able to get exceptions from the building code department, and those are things that other architects, other developers have been able to use, and now they're no longer problems in the city. Supply chain, you'll see here, I've circled it in each project. Each project supply chain has always been an issue. And supply chain on Cornell Tech, obviously it was at that scale at that time, and there's a lot of issues getting certain materials. But over time, while supply chain is still an issue, it's getting better and better. Like the same way that like codes are increasing and architects, we're all asking for more products from manufacturers. They're rising. The market is rising to meet that demand, which is fantastic. The other thing I'll just point out is that these are incredibly dense buildings. Your source EOI target needs adjusting. What was great about Cornell Tech is that we started getting data from that, and we're able to start adjusting the density, the EOI targets on other projects based on like real world data. And then one thing just to note, this, as an office building, even in Boston, it's cooling demand driven, even in that climate zone. Here's some plan examples, comparisons. You can see our original design budget here was 38.1 kilobtu's per square foot per year. And that was the same when we got to Sendero A, but then by the time we started working on Sendero B, like the density calculator started to kick in, and we were able to start adjusting for how dense, how many refrigerators, how many people are being packed into this space. I'll also point out like the density on Winthrop Center, like it's kind of weird. It's like half density in a way, because like from 9 o'clock in the morning till 6 o'clock, it's incredibly dense, and then everyone kind of goes away. So we put the people per square feet in here so you can see what that is. And obviously once you get up to University of Toronto, you're in climate zone 6, so the energy budget increased there as well. And then just a quick section study here, so you can see how the passive house standard allows for different certifying pathways. Cornell, the whole building is certified. The entire exterior wall is the airtight boundary. On Sendero Verde, the affordable housing is the certified areas, but the entire building is enclosed by the airtight envelope. The community facility spaces have been pulled out of the certifying boundary, but they still have an airtight facade. That's because tenants are community facilities, they're nonprofits. They may not have the budget initially to meet passive house, but we want to allow them that choice to opt in. On Winthrop Center, the office component is the passive house certified and airtight layer boundary. And then there are some discussions to include the entry lobby as part of that certifying boundary, but this is now out, so I need to update the slide. And then UTSC is very similar strategy to Cornell Tech, with the exception that we pulled out a loading dock area. But being an undergraduate dorm, I just want to point out there's a dining hall here, and so you start having conversations about reducing energy use. You start saying, hey, can we go meatless Mondays, or you start talking to the vendors and be like, okay, you can have one walk but not two. Those are the types of conversations that we end up having in programming phase. So with that, I'm going to turn it over to Louis to talk about the facade.
Yeah, thanks, Ryan. I'm Louis Kale, Handel Architects. I've been working with Ryan for many years now on many of these projects. So the facade is obviously a critical part of any passive house. So we're going to talk a little bit about some of the challenges we met here. So what we like about looking at all these projects together is you can kind of see that there's 5 different facades for 4 different buildings. So a lot of different ways to get to the goal. We say 5 because Sendero Verde actually has 2 different facade systems. We're using a masonry cavity wall for the tower for building A, and then there's an EFIS facade for the shorter buildings. So at the house at Cornell Tech, we had a mega panel rain screen, shop fabricated, shipped to the site, hung from the slab like a curtain wall, these big panels that are 30 feet long, 10 feet wide. I mentioned Sendero. At Winthrop, we have a curtain wall, which was an interesting challenge. And then at the triple glazed curtain wall, all these projects have triple glazed windows and curtain wall. University of Toronto is a stick built rain screen. You can see all of them, or at least the 2 New York projects have an R value, and the walls are around R20. In Boston, because of the different occupancy and different climate zone, we're landing around R18, and then it's a little bit more well insulated in Toronto because it's in that climate zone 6. With Cornell being our first passive house, windows, as Mariah mentioned, supply chain was a challenge. Windows were a significant challenge on this project. We managed to get to a 0.18, which was, very, very impressive for that time. On Sendero and University of Toronto, we're managing to get a little bit lower by using UPVC windows. And then obviously the curtain wall is its own unique challenge there in Boston. You can go to the next one there, Ryan. So we'll take a look at some of the wall sections here, and just won't dive too deep into this, but starting over there on the left, you got Cornell Tech. You can see the panel joint there between the mega panels. And then next to that, you have Sendero Verde A. And then all the way on the right, I'll call it University of Toronto. So all three of these use steel studs as kind of the backup system for the structural system for the wall. And those steel studs are infilled with mineral wool insulation, and then they have mineral wools in the cavities in the kind of rain screen system or in the brick cavity. So it's kind of similar logic, but different aesthetic. Obviously different challenges with the brick. You had the shelf angle, and with UTSC and Sendero Verde, you have the slab penetrating that steel stud layer. Sendero B, we used EFIS, which is a challenging material aesthetically, but thermally it's fantastic. There's no penetrations, no metal attachments. You can actually extend it over the windows, which you can kind of see we're doing there, which helps improve your window install details. So you can see really this is the one section here where you don't have any interior insulation because it is so efficient on the exterior. It's 4 to 6 inches of EPS versus 9 to 12 inches of mineral wool everywhere else. Winthrop Center, we have heavily insulated spandrels, and both vertically and horizontally, and then a little bit additional insulation on the inside of that. You see two control layers here. The blue line is our air barrier, and the green line is a vapor control layer, controlling moisture because of having the insulation on the inside of that air barrier. In all of these projects, the passive house airtight layer is that blue line, with the exception of Cornell. And that's primarily because of that panel joint. So go ahead to the next slide. We see these panels being, craned into place here. This is a wet joint system. So we couldn't seal the building up until all the panels were installed, which obviously made it very difficult to test any portion of the building and make sure that we were doing this correctly. So that was a big reason why we put the airtight layer on that interior layer, because it wasn't inside the panel. So if you go to the next slide, so we could actually see the layer and access it, make any repairs that were needed. You could seal everything up around the anchors as each panel was installed, and then we could do guarded blower door tests on individual floors or sections of the building to make sure that everything was going along as planned and there weren't any surprises at the end of the project. Go next. So another thing, obviously another challenge that you deal with on all passive house is thermal bridging. This is just a kind of a smattering of some unique details that we looked at here. On the left there, you have a structural thermal break between a steel canopy. We're using kind of these similar structural thermal breaks up on the top two on the right there, where we have shook isocorbs below concrete curbs underneath the generator, and then general plastics below steel dunnage for our PV array. Next to that on the left there is our shelf angle detail. You can see we just barely make out the shim there. So we're using an Armatherm FR shim, which is just a thermal shim. It's 3/4 of an inch to an inch. We looked at standoff shelf angles and other systems, but this was the kind of most cost-effective conventional practice. We weren't throwing the masons through a loop here. We were trying to get something that they knew how to construct, and this got us to our performance targets, with really high-performing windows and additional insulation in the walls. And then down on the lower right there, this is a good one that we are using everywhere now on all of our projects. We're trying to get into all of our projects. We're using 2 courses of AAC block at the bottom of all of our parapets. We also use it to support brick when the brick is at that grade. And that, because that AAC block is less thermally conductive, it creates a thermal break, and you no longer have to wrap your parapet in insulation. It makes the waterproofing easier. It's cheaper, and it works within a CMU module. So you can, the masons can throw that thing together just like they would a typical parapet wall. So you can go next. So Ryan mentioned supply chain challenges. One of the big, this is just a good anecdote. On Cornell there on the left, we had a condenser porch on every floor, and we really struggled finding a thermally broken door to access that porch. And so there just wasn't a good thermally broken door on the market at that time. So what the team ended up doing is using like a deli door, like a big refrigerator door, which gave us an R28. So plenty of insulation, but obviously not the most conventional detail, and much more expensive than a typical door. Over on the right there, you see once we got to Sendero, the market had adapted, and now there is a thermally broken hollow metal door and frame on the market. We only need that R2.5. It's not a huge difference from. It definitely doesn't need to get to that R28, but just that little bit. When we work through the installation details, we can make that work with our model. Go next. And then the last thing that we are starting to consider with Sendero Verde and other projects, we're really trying to start to think about embodied carbon and how that plays into our projects. It's not a passive house requirement, but it's something that as we build more and more insulated buildings, we get more and more refrigerant in our buildings. We need to start thinking about how these materials impact the embodied carbon of our buildings. So one thing that we committed to is trying to use mineral wool insulation wherever possible, because there is, XPS insulation has such a high carbon emissions. So we used XPS nowhere except for foundation walls where it was kind of required. With the EFIS system, we really pushed to get a mineral wool system. The market didn't quite get there. We weren't able to use a mineral wool EFIS system, which exists in Europe and Canada, but doesn't exist in the US market. Stowe has since introduced one, but not in time to get on this job. So we used EPS. So we sacrificed a few points on our R value to save some carbon emissions. And then of course, we're all looking forward to the day when we can grow our own insulation there with the mycelium. Hopefully that'll be in all our projects one of these days.
And so here we are, a robust facade and efficient and balanced heating and cooling with energy recovery. And what we've just done is reduce the energy use in our building from 130 EUI, that's based on a 2018 New York City standard, down to about 38 to 50 EUI, depending upon your density. But also notice what happens to the slices of the pie. Before we were spending almost 50% of a much larger pie on heating and cooling. Now we are only spending 10% of a much smaller pie on heating and cooling. So for us, it like begs the question, what is the next lower hanging fruit? So we're starting to focus on domestic hot water demand, lighting, plug loads, and like Louis mentioned, the embodied carbon. And the work is happening. Here are some construction images of the Sendero Verde project. You have building B North and B South, they both topped out. B South is just starting to receive its EFIS finish coats, and it's about a year left until residents can start moving in. Building A is this site over here in the corner. We're just closing this phase in June, and construction is slated to start in September. And at the end, you get a beautiful building. Your client is happy, and you're saving the earth. But don't forget about a couple other important reasons why we like passive house as a main strategy towards green building. And that's because passive house can enhance the occupants' lives. There's an acoustical quality, a quietness to the space. The interior and the exterior is air sealed and insulated. This is the Queensboro Bridge in the background of this image here. That's eye level with some of our units. Our 15th floor is eye level with Queensboro Bridge. That's rush hour traffic twice a day. Just imagine the noise. New Yorkers like to honk their horns. And it just, when you shut those windows, you don't hear anything. And it's so like passive house is ideal for these noisy and urban environments. And what it allows, it's this quietness that's important for mental health. Passive house is about a comfortable temperature and thermal criteria, options for control. Of course, we can open our windows. It's about low cost for heating and cooling. In a conventional building, air conditioning may cost upwards of $150 a month in New York City. Now, what if that cost is reduced down to $10 or $15? Well, that choice is a lot easier and can really impact people's lives. And for us, this really starts to speak to equity in green building. And just to reiterate, we are also providing healthy filtered fresh air 24/7. This increase of interest in health and wellness is a main driver that we're seeing not only with our clients, but one of the main places we are seeing concern for green design concepts starting to percolate into the general population, affecting marketing and leasing too. And just to conclude, at Handel Architects, obviously you could tell by the talk, we feel passive house is one of the best strategies we have to protect this house.